Throughout much of the first part of this course, we spent a good deal of time describing subsets of a space, either as the solution space to a linear system of equations, or as the span of a set of vectors. As we've been doing this, we've been sort of implicitly using language about the size or the shape or maybe even the dimension of a subset of some space. Now that we understand the notion of basis and of a coordinate system, we're going to formalize some of this language. The first step is to define a subspace. A subspace of Rp is a non-empty set, V, contained in Rp that satisfies the conditions 1. For every pair of vectors u and v in this set, their sum, u plus v, is also in the set. We say that v is closed under addition. And 2, for every real number a and vector v in our set, the scalar multiple av is also in our set. We say that v is closed under scaling. Note that by 2, every subspace of Rp must contain the zero vector. There is necessarily some vector in our set, v, and we are allowed to scale by any real number. Since 0 is a real number, 0 times v gives us a zero vector. Closure under scaling tells us that is also in our set. So the most obvious subspace that we can describe is Rp itself. Every set is a subset of itself, and we know that we can add two p-dimensional vectors and get a p-dimensional vector. We can also scale a p-dimensional vector and get a p-dimensional vector. So because the p-dimensional vectors are closed under addition and scaling, they form a subspace. The next type of subspace that we can form is the span of a set of vectors. This is the most natural type of subspace that we can construct. So let's consider the following three vectors. U has coordinates 2, -1, and -2. V has coordinates 0, 3, 1. And W has coordinates 4, 4, and -2. These are three-dimensional vectors, so of course their span forms a subset of R3. Explicitly, to check that this is in fact a subspace of R3, we want to show that if we have a vector x, which is a linear combination of u, v, and w, a vector y, which is also a linear combination of u, v, and w, and a real number r, that we can add these two vectors together and get another vector, which is a linear combination of u, v, and w. And we can scale either of these vectors by r and get a linear combination of u, v, and w. For addition, we note that when we add these two vectors, x and y, together, we simply add the coefficients. And so x plus y is, in fact, an element of the span of u, v, and w. For scaling, we note that we simply distribute the scalar to each of the weights. So this tells us that, in fact, the span of these three vectors is a subspace of R3. Now, when we talk about the span of a set of vectors, we're oftentimes interested in the reduced row echelon form of the matrix with our vectors as columns. For this matrix, we can see directly from the reduced row echelon form that our third column, W, is actually able to be expressed as a linear combination of U and V. Namely, W is twice U plus twice V. So in our previous discussions on the span of a set of vectors, we would have declared that this set describes a plane in R3 because there are exactly 2 rows with a pivot position. Now that we have a proper notion of basis, we can understand why we made this declaration to begin with. We've already noticed that the reduced row echelon form tells us that W can be expressed as a linear combination of U and V. This tells us that the span of our 3 vectors U, V, and W is actually the span of the 2 vectors U and V. The reduced row echelon form of the matrix also tells us that the columns corresponding to U and V have a pivot position. Since both of these columns have a pivot position, we know that the vectors U and V are linearly independent. So we note here that these 2 vectors, U and V, actually span the subspace V and are linearly independent. If, for example, V were equal to R2, we would claim that these vectors U and V were a basis. So we define the basis for a subspace V of Rp to be a set of vectors that span V and are linearly independent. We're also going to mimic the definition of dimension for spaces that look like Rp, and we're going to say that the dimension of a subspace V inside of Rp is the number of vectors in a basis, and we'll write this as dim V. Now it's important to note here that because V is a subspace of Rp, and Rp has a basis with p elements, i.e. it is a p-dimensional space, all of the subspaces must have dimension at most p. And in fact, this definition allows us to characterize all the subspaces of Rp as the m-dimensional subspaces, where m is at most p. So for example, let's do R1, R2, and R3. R1, which you could just regard as the regular old real numbers, is one-dimensional. That means there are 2 possible subspaces of R1. The first one has only the 0 vector in it and is 0-dimensional. Every other element of R1 will generate a one-dimensional subspace, which is R1 itself, as all of its scalar multiples, or the span of that element. So this tells you that the vector space R1 is very simple. For R2, there are 3 possibilities. We always have the single 0-dimensional subspace consisting only of the 0 vector. We can construct one-dimensional subspaces simply by taking a non-zero vector and considering its span. The third type is all of R2, which comes from the span of 2 linearly independent vectors. And as you might guess, if we jump to R3, then we'll have 4 subspaces. The set containing only the 0 vector is the only 0-dimensional subspace. We obtain a one-dimensional subspace as the span of any non-zero vector. This is, of course, a line in R3 through the origin. If we choose 2 linearly independent vectors, we'll get a 2-dimensional subspace, which is a plane through the origin. And of course, if we choose 3 linearly independent vectors, u, v, and w, they form a basis for R3, and their span is a 3-dimensional subspace, or R3 itself. And of course, if you're interested in classifying the subspaces of Rn by dimension, you can keep playing this same sort of game. You'll always have the 0-dimensional subspace with just the single 0 vector in it. a one-dimensional subspace, which is the span of a non-zero vector, two-dimensional subspaces, which are obtained as the span of two linearly independent vectors, etc., until you get to the n-1 dimensional subspace, which is the span of n-1 linearly independent vectors, and finally, Rn itself, which is the span of any n linearly independent vectors, also known as a basis for Rn. So in the next video, we're going to spend some time discussing some important subspaces.